I have really exciting news for you. This video is very short and very easy. Yay! I appreciate that the last one was the opposite in both senses. It was really long and it was quite complicated. I did say in the email that in my opinion the module gets a little bit easier from that point, and I'm not going back on that. So don't panic, ladies and gents. Take a breath, you should be fine. Okay, we are on pages 28 and 29 of your Tectonics module booklets. If you don't have page numbers because you've printed it, you want to find a page that says the Volcanic Explosivity Index, open brackets, VEI, close brackets. And it's just 2 pages, which is all we're going to talk about in this video. Okay. If you have done anything on earthquakes at all, or even if you've never studied earthquakes, but you've just watched the news and kind of maybe interested, you have probably heard of the Richter scale. And the Richter scale is the measurement of magnitude of earthquakes, and it's quite widely known among the general public. For reasons I don't fully understand, the VEI, which is the equivalent of the Richter scale for volcanoes, is not very widely known. Not that that matters, it's just interesting. So it's basically, if for revision purposes, the VEI is the Richter scale for volcanoes. It's the way that we measure the kind of size of their eruption. Now, interestingly, it isn't on so the Richter scale measures the actual magnitude of the earthquake. This is slightly different because it tends to measure the amount of stuff that comes out of your volcano. So it is a slight variation. And if you have a look at pages 28, 29, we've given you a text version and we've given you a visual version. But I just want to click through some slides to prove to you that there are loads of variations. So there's one on the screen. That's very similar to what you've got on page 29. There's a different version. There's a different version. So what I think you might want to do, and of course feel free to try and find one on Google that you like, I think you need first of all to find which version of the VEI makes the most sense in your brain. All right, I do not mind whether you go for a visual version or a text version, it doesn't matter. Whichever one makes the most sense to you. Because as long as you've got the VEI numbers, and as long as you've got some key differences between them, that's all you need. Okay? So, what do we need to know about the VEI? Well, I've told you which pages of the module it's on already. Above the table on page 28, it does tell you in the third paragraph, each interval on the scale represents a 10-fold increase in observed eruption criteria. That is very similar to the Richter scale, and I will teach you properly about logarithmic scales when we get to earthquakes. Some of you might know about logarithmic scales from maths or physics already. Essentially, if you look at the VEI and you look at, say, let's go back, let's do it on here. So you might think to yourself, I don't think the difference between 0 and 1 on the VEI is that big a difference. Well, actually, it's about 10 times bigger. And in fact, that's why I quite like this version, because it kind of sort of gets that across to you quite nicely, that there's actually quite a big difference. You might prefer that one. It's fine. It's not a crucial thing to know, but what it means is if you are comparing a volcano that is VEI 3 with a volcano that is VEI 7, they are completely different kind of eruptions. They're not in any way similar. The numbers are more different than perhaps you first appreciate. But like I say, we'll talk about that quite a lot more when we get to earthquakes and talk about the Richter scale. Really, all you need to do is to notice the patterns. The text version is slightly better for this in some places than others. So let's have a look here. Okay, so the VEI goes from 0 to 8, fine. Notice that the amount of stuff that comes out of your volcano, and a posh way of saying that is ejector volume, that's the volume of material that is ejected or erupted from your volcano. Look how much bigger it gets. I mean, personally, I can't even imagine 1,000 cubic kilometres. That's just, it's too big a number for my little brain to cope with. But you can very clearly see that the amount of stuff that comes out of your volcano goes up quite considerably. We know a little bit about this from the last video. We know that Hawaiian volcanoes don't have ash clouds because they don't have big explosions. We know that Plinian, remember that type of eruption is named after a person because he described the eruption of Vesuvius. Plinian is a massive ash cloud. Yeah, okay, so that sort of links to what we learned last time. Effusive eruption, no explosion, no ash cloud. Mafic magma, no build-up of pressure. And then it gets worse. I love some of these words. I shouldn't, but I don't know that I could tell you the difference between mega colossal and apocalyptic, but there you are. Anything from here on looks pretty horrific to me. But anyway, you get a nice little adjective of how bad things could be. This is the height of the plume. So in the case of this one, that would generally be lava fountains, possibly lava bombs, that kind of thing. This is going to be ash clouds. So you can also see that as the VEIs go up, the ash cloud gets bigger. Well, that makes sense, doesn't it? If you've got more stuff coming out of your volcano, it's going to go higher up in the atmosphere. That's fairly logical. But notice that there is also a negative relationship. As the numbers go up, the frequency goes down. Constant, daily, weekly, every few months, once every 10,000 years. And you honestly know, or are beginning to know, why that happens. And it's all back to our lava types once again. So we've said that with mafic magma, which is the type we're going to get down here, because it's not viscous, so it's quite runny and your gas can just constantly escape, you get this nice sort of spurting volcano, lots of lava, very pretty, no build-up of pressure, no explosion. In order to get the size of explosion that you are going to describe as colossal, you need the pressure to build up in your volcano for a really long time. So you've got your nice thick silica-rich viscous magma, which means that the gas bubbles cannot escape. So the gas bubbles build up and build up and build up. Now, if they build up over 100 years or more, you're going to have a pretty big explosion. If pressure has been building for 10,000 years, it doesn't take a geographer to work out that that's going to be a much bigger explosion. Okay, so it very much links to the quite tricky stuff that we learned this week. But really, you just need to know that it exists, that the difference between the numbers is much bigger than first anticipated, and just to have a sense of, as the numbers go from 0 to 8, what increases and what decreases. So I've put a little note on there, okay? So as the VEI goes up, the volume of eruptive material and height of plume goes up, so there's a positive relationship there, but the frequency and the number of occurrences go down. To be honest, folks, number of occurrences is... oh, sorry, that's in your version on pages 28 and 29. That's how many times do we know that we've had eruptions of that magnitude, of that size? Well, it kind of follows, doesn't it, that the less frequently something happens, the fewer occurrences we are going to have known about. And that's it. That's the VEI. Remember, we are having our final question and answer session on Monday with Nick at 2 o'clock. I've tried to get all the tricky stuff done before that to give you an opportunity to bombard him with lots of difficult questions. It doesn't mean you can't email your teacher at all, but I think all the tricky stuff has done for now, ladies and gents. If you're with me so far, brilliant. You've done really, really well. Congratulations.